welcome back. In the last session of neural network, we have gone through one of the simple single layer neural network known as perceptron, and also we compared MP neuron with the perceptron. Let us have a recap of perceptron and the learning algorithm that we studied in the last session, and then we'll move ahead with the new contents. So, perceptron has a single neuron and it accepts the inputs x0, x1 up to xn, where x1, x2 up to xn, that means n inputs are representing the features of the training sample. X0 is the additional input that we have added. X0 is always equal to 1. So, we are having n plus 1 inputs, and every input is associated with a weight W0, W1 up to Wn. So, we are having now two vectors x and w comprising of n plus 1 elements. W0 is actually meant for threshold. So, W0 is equal to minus theta, and this input along with this weight W0 is actually added because we wanted to learn the threshold also. Here function g is actually computing the weighted sum, and f is a function that works on g, and f typically is a thresholding function which is also known as the activation function. Using this perceptron, actually we wanted to learn the weights. So, we have gone through the perceptron learning algorithm or the perceptron rule. So, let us only focus on the key idea in the perceptron rule. So, we go on presenting the examples in our training data set one by one, and we update the weight vector if required. So, we initialize the weight vector randomly, and we also initialize the learning rate eta initially, and then we go on iterating through the algorithm. So, the key idea here is we would like to update the weight vector if there is a mismatch between the class of the training example that we presented. So, if there is a mismatch in the actual class or actual label and the observed label by the perceptron, then we update the weights, otherwise we'll go to the next sample, and we repeat this process until we learn all the training examples. That means the convergence of the algorithm is when all the training examples are classified correctly. So, formally we may say that update the weight vector if actually the sample is positive and observed as negative. So, in this case we update the weight vector as w equal to old w plus eta into x, and if actually the sample is negative and observed as positive by the perceptron, then also we are going to update the weight as W equal to W minus eta x. As I mentioned, eta is the learning rate, which is a small positive constant. If training data is linearly separable, then perceptron rule works well and finds a weight vector. If training data set is not linearly separable, then perceptron algorithm will not converge, and hence we need to do something extra. So instead of the original perceptron learning rule, we may go for a delta rule that uses gradient descent, or even for more complex problems we should go for multi-layer neural network. So let us proceed with delta rule. The key idea behind delta rule is to use gradient descent to search the hypothesis space of possible weight vectors to find the weights that best fit the training examples. In fact, we know the gradient descent algorithm that we have seen earlier to minimize the cost function or the objective function in earlier ML algorithms such as regression. Thus, gradient descent is an optimization algorithm that approaches a local minimum of a function by taking steps those are proportional to the negative of the gradient of the function at the current point. Though we know how gradient descent works, let us have a visual explanation for the concept. So let us assume that we are having a weight, and that is denoted as the horizontal axis, and we are computing the cost function, for which the parameter is the weight, that is W. So we are computing the cost function J of W, and if we try to plot that cost function against the parameter W, then we are having something like this. Please look at this slide. We are having a parabolic representation, something like this. So this is a convex function, and we are interested in finding the gradient of this function. So how to compute this gradient of J of W? So gradient is nothing but the derivative of the function J of W. So let us assume that we are having one point here, then we can draw a tangent to that point, and we calculate the slope of the tangent that is drawn at that particular point. This slope is actually nothing but the derivative or the gradient at that point, and we move in the negative direction to the gradient by updating the weight with a small value, and we continue this process till we reach to this minimum. This is the minima. So we continue the process till we reach to this global minima of this cost function. In fact, we had a detailed discussion about gradient descent earlier. So in a sense, here what we are going to do is we are going to calculate the derivative or gradient of the cost function with respect to the weights, and then change each weight by a small increment in the negative direction to the gradient. And this is how, considering all the weights, we are going to apply gradient descent to reach to the global minima. This rule is important because gradient descent provides the basis for the more advanced backpropagation algorithm which can learn networks with many interconnected units and layers. Now, please note that while dealing with perceptron, we used earlier the activation function as the thresholding function, and if we would like to apply gradient descent, we need an activation function that can be differentiable. For example, such a differentiable activation function is like a linear function. For example, f of a is equal to a is a linear function, and that is a differentiable function. So, to apply gradient descent, we need such kind of a function instead of the thresholding or step function that we used earlier with the perceptron. So, we need to change our activation function. Now, after selecting our activation function, what next we would like to do is, by making use of this activation function, now we are going to compute the output of our perceptron. So, let us define now the cost function. The cost function is nothing but the sum of squared error. So, the cost function j of w is represented as half summation over d, small d belongs to capital D, yd minus yd hat whole square, where yd is the actual label of the sample D in training data set and yd hat is the observed output of the perceptron for the same sample D. So, as usual, we are finding out the error between the actual target label and the label that we observed using the perceptron, and we are finding out the sum of squared error which defines our cost function. And once we get the cost function, this cost function can be minimized to update our weights. In this cost function, we are having this fraction half. So, sometimes it is used, sometimes it is not being used, but this fraction half is just used for mathematical convenience to have a nice form of the expression, and that would be helpful further whenever we go for finding the derivative of the expression. Thus, we would like to minimize this cost function j of w. So, we are going to compute the partial derivative of the cost function for each weight in the weight vector. So, while computing the gradient descent, what we need to do? We need to minimize our cost function. And how we represented our cost function? It is j of w, it is a function of weight vector, and that is equal to half summation over small d belongs to capital D, yd minus yd hat whole square. So, here capital D is set of training examples, small d is individual sample in the training set, yd denotes the actual label associated with sample D, and yd hat is the observed label of sample D, and we are finding the sum of squared error as the cost function j of w. And to minimize this j of w, we are computing the gradient of this function j. So gradient of j is nothing but derivative of j with respect to the weight vector w. So w is having several components, say w0, w1 up to wn. So gradient of j or derivative of j is denoted as del j of w, and it is a vector whose components are actually the partial derivatives of j with respect to each of wi's. So it is a vector comprising of partial derivative of j with respect to w0, partial derivative of j with respect to w1, and so on up to the partial derivative of j with respect to weight wn. So here n denotes the number of features in our feature vector. Now what we would like to do is, we would like to follow small steps towards the minima. So we need to use a training rule for gradient descent to update the weight vector w. And how we are going to update this weight vector w is, we are updating w as w plus small change in w, and that is denoted as delta w. So w is equal to w plus delta w. And how this delta w is being computed? This delta w is equal to minus eta times del j of w. As we know, this eta is the learning rate, which is a small positive constant that determines the step size in the gradient descent search, and typically this eta value is small, so that by making tiny steps we can reach to the minima. Here we are having this negative sign because we want to move the weight vector in the direction that decreases j. So I'll repeat once again, the training rule for gradient descent is making some small update in the weight vector. So new weight vector gets updated as old weight vector plus a small value, small change in w denoted as delta w. So w equal to w plus delta w, and this delta w is represented as equal to minus eta times del j of w. Whenever we say that we would like to update the weight vector, meaning we would like to update individual element of the weight vector, and thus we can write the training rule in component form as well. So the training rule in component form can be written as wi is equal to wi plus delta wi. So here we are updating individual weight wi with small change in the respective weight factor. So wi is equal to wi plus delta wi, and here delta wi is represented as minus eta times partial derivative of j with respect to weight wi. Thus each component of vector w needs to be updated by this update rule. Further, this partial derivative of j with respect to wi is computed with this expression. So partial derivative of half summation over d that belongs to capital D, yd minus yd hat whole square with respect to wi. We are not going into the details of solving this expression, but finally what we get is the partial derivative of j with respect to wi is equal to summation over small d that belongs to capital D, yd minus yd hat into minus xid, where this xid denotes ith input component or ith individual feature of training example denoted as small d. And now by simply substituting this partial derivative of j with respect to wi in our earlier expression for delta wi, we get now the expression for delta wi equal to eta times summation over small d that belongs to capital D, yd minus yd hat into xid. So as I mentioned, this xid is the ith input component or ith individual feature of training example. So we are having x0, x1, x2 for as inputs for the perceptron. So this xi is nothing but that value for a particular sample D. So now let us summarize the algorithm that we discussed. So the gradient descent algorithm for perceptron learning. So let us systematically formulate the algorithm. The algorithm has the input, that is the training set D, which contains the examples of the form x comma y, where x is a feature vector describing one example and y is the associated label. Next, we initialize the weight vector w randomly. Also, we initialize learning rate eta with a small positive constant. This is also an iterative algorithm. So we are having the while loop. So while not convergence, we are iterating through. So here the convergence condition is to reach the minimum error, as we are minimizing the error in gradient descent. So under the iterative loop, we are having the first step to initialize each delta wi to 0. For each sample x that belongs to capital D, do compute output y hat. For each weight wi, compute delta wi. So how we are computing this delta wi? Delta wi is equal to the old value of delta wi plus eta times y minus y hat, that is the error, into xi. Xi is the respective input to the perceptron for that particular training example x. So for each weight wi, we are computing this delta wi for given sample capital X. Now with these computed delta wi values, we are going to pick the next sample from the training data set, and once again we are going to repeat this process, and once again for this input sample we are going to compute the delta Wi values. So this is how in this step number 2 what we are getting is, we are getting the delta Wi values after going through the entire data set, after going through the computation for all the examples belonging to the training data set D. So once we get these delta Wi values, third step comes in. So what we are going to do next is, for each weight Wi, now we are going to update all those Wi's simultaneously. So Wi is being computed as old Wi plus delta Wi that we have computed in step number 2. So this is how we are going to update Wi's, and we are going to repeat this entire process again and again. That means we are iterating through the entire training data set again and again to come up with the weight vector, final weight vector that optimizes our cost function. So this is how we formulated our gradient descent algorithm for perceptron learning. Please note, this algorithm works well for a decision surface that has a single global minima, and because the error surface contains only a single global minima, this algorithm will converge to a weight vector with minimum error, regardless of whether the training examples are linearly separable, given the sufficiently small learning rate eta. If eta is too large, the gradient descent as usual runs the risk of overstepping the minimum in the error surface rather than setting into it, and hence the algorithm may diverge if we are having eta which is too large. Sometimes there is one common modification to this algorithm, and that is to gradually reduce the value of eta as the number of gradient descent steps grows. I hope you have understood this algorithm. So please go through this again. Even though gradient descent is an attractive algorithm for perceptron learning, there are certain problems with gradient descent. Converging to local minimum may sometimes be quite slow, and it requires thousands of gradient descent steps. This is one problem. Secondly, if there are multiple local minima in the error surface, then there is no guarantee that the procedure will find the global minimum, and hence some modification has been proposed in the original gradient descent algorithm, and the new algorithm is known as incremental gradient descent or stochastic gradient descent algorithm. So let us see now the stochastic gradient descent algorithm. The gradient descent training rule presented earlier as delta Wi equal to eta times summation over d that belongs to capital D, yd minus yd hat into xid. This computes weight updates after summing over all the training examples in training set D. Instead, the idea behind stochastic gradient descent is to approximate this gradient descent search by updating the weights incrementally following the calculations of the error for individual example. So instead of computing the error for all the samples in the training data set in stochastic gradient descent, it is approximated by updating the weights incrementally with the help of computation of the error for individual examples. Thus, the training rule in stochastic gradient descent is modified as delta Wi is equal to eta times y minus y hat xi. Here, y is the label associated with sample capital X, y hat is the observed output by perceptron, and xi is the respective input. So let us try to systematically write this algorithm for stochastic gradient descent. So here once again we have the input as the training set D having the samples of the form x comma y, where capital X is the vector that denotes the features of that particular training example, and y is the known label associated with this vector x. We are going to initialize weight vector w randomly. Also, we are going to initialize learning rate eta with some small positive constant as usual. This algorithm also iterates through till the convergence is not reached. So here once again the convergence means reaching to the minimum error. So here we are having the simplified algorithm, and what we are going to do here is, in step number 1 we are initializing each delta Wi to 0, and in second step we are having the iterations through the entire training data set. For every sample X in training data set D, we are once again computing the output y hat, and for each weight Wi, we are directly updating this Wi as Wi plus eta times the error y minus y hat multiplied by input xi. So here this term, that is eta times y minus y hat xi, is nothing but this delta Wi. So the training rule here, that is delta Wi equal to eta y minus y hat xi, is modified, and that is that this delta Wi is being added into the old value of Wi. Please note here, in contrast with the earlier gradient descent algorithm, here we are computing the error for individual example, and immediately after computation of the error we are updating the weight Wi. Thus, after computing, or rather updating the weights for one particular example, one particular training example. We are going to the next example and using the earlier computed WIs, we are going to update once again the weights with respect to the new training example, and thus we are iterating through all the training examples in our data set, and this entire process repeats again and again till the convergence. I hope you must have understood the difference in these two algorithms. So one way to view this stochastic gradient descent is to consider a distinct error function JDW defined for each individual training example D. So JD of W is equal to half YD minus YD hat whole square. So instead of having the sum of square error for the entire data set, we are considering the error for individual training example, and this particular cost function we are trying to minimize. The training rule delta Wi equal to eta times y minus y hat into xi is popularly known as delta rule, or few other names for this rule are the Adaline rule or Woodruff rule. So this name suggests the names of the inventors of this algorithm. So this is delta rule. So if we try to compare these two algorithms, gradient descent and stochastic gradient descent, we are having listed here few points. So under gradient descent, the error is summed over all examples before updating the weights, whereas in stochastic gradient descent, weights are updated upon examining each training example that we have already seen in the discussion of both the algorithms. The next comparison we may have is like in gradient descent, summing over multiple examples requires more computation per weight update step. Repeat, summing over multiple examples requires more computation for updating every weight. The stochastic gradient descent is often used with a larger step size per weight update. The third point of distinction is like gradient descent cannot handle multiple local minima. So when the cost function is convex and having a single minima, that is a global minima, the gradient descent algorithm is preferred. As far as stochastic gradient descent algorithm is considered, it uses individual error of an example rather than having summation of errors for all the examples, and hence can sometimes avoid falling into local minima, and mostly it reaches to the global minima even though multiple local minimas are available in the cost function. So we have had the comparison between gradient descent and the stochastic gradient descent algorithms, and now we are having the comparison between the perceptron learning rule that we have discussed in detail in the last session and the delta rule that we have discussed in this particular session. So, under perceptron learning rule, the activation function is thresholding function, or sometimes it is called as a sign function. So, we are having some threshold and we compare the output with that threshold, and depending on whether it is greater than the threshold or less than the threshold, we assign the class to the sample. And in this perceptron learning rule, the weights are updated based on error in the thresholded perceptron output, whereas in delta rule, the updation of weights is based on the error in the unthresholded linear combination of inputs. As delta rule is based on the gradient descent algorithm, we need a function that is differentiable as an activation function, and hence instead of thresholding function, we need to use a function like linear function of the form f of a equal to a. Next, perceptron learning rule converges after some finite number of iterations to a hypothesis that perfectly classifies the training data, provided the training examples are linearly separable. If we look at delta rule, it converges towards the minimum error hypothesis, and it may possibly takes unbounded time, but the algorithm converges regardless of whether the training data are linearly separable or not. So these are the major differences between perceptron learning rule and the delta rule that we have studied. So now we know that perceptrons are very basic single layer neural units, and we have gone through various algorithms to learn perceptrons. Though the learning algorithms are available for perceptron learning, it is not possible to model complex nonlinear functions using single perceptrons. Thus, we need to extend this concept of perceptron to the higher level, and hence in the next session we are going to discuss about multi-layer neural networks and the popular backpropagation algorithm. So that's all for today. Thank you.